3.9 is related rates. Implicit differentiation can be used to find rates, derivatives, with respect to time when writing equations that are not explicitly defined in terms of time are possible, or not enough information is available to find rate with that equation. So that's kind of in the abstract, and we'll obviously do a bunch of examples, and I'll start out by just giving you some guidelines here. It says identify what you are asked to find, make a sketch, and identify the given. Imagine the sketch in motion to determine which dimensions and quantities are constants, and those are things that do not change with time in this application. And you're also trying to identify which are variables. These are things that change with time. So the dimension is getting bigger or smaller, longer or shorter, I guess I should say. Volume is getting greater or less, things like that. Try to use symbols, meaning variables or constant names, to represent what you're trying to find in any given rates. And remember, rates are derivatives with respect to time. Second guideline is to find an equation, or in some cases equations, that relate the variable in the rate you are trying to find, without the t in the rate part, with other dimensions and given quantities. Remember, any variables change with time in the equation will reproduce a rate after you take the derivative, with possibly a byproduct of that variable. And so if there's more than one equation, you need to combine the equations in this step to reduce it to the variables that change with time and that the rate is accounted for. Guideline 3, use implicit differentiation and take the derivative with respect to time of both sides, because we're trying to find rates, which are derivatives with respect to t, and we're given some rates. So that's how we get that equation. And when you do this, it's very important that you realize what is a variable with respect to time and what is a constant, something that doesn't change with time, because their derivatives are going to depend on that. A derivative of a constant is going to be 0. Guideline 4, substitute in known quantities from the given. Sometimes needed quantities were not given but can be found easily by relating the equation to other known quantities for that particular time at which you're trying to figure out this rate. And so you solve for that rate and you're done. So we'll start with example 1. Air is being pumped into a spherical balloon at a rate of 4.5 feet cubed per minute. Find the rate of change of the radius when the radius is 2 feet. So I'm going to start out by drawing a little picture. Nothing too complicated here. Just trying to draw a balloon that is being pumped with air. And it's a spherical balloon, so I try to draw that as close as I could to a circle. It says that air is being pumped into the spherical balloon at a rate of 4.5 feet cubed per minute. And so down here by the pump, maybe I want to indicate this rate here is 4.5 feet cubed per minute. Find the rate of change of the radius when the radius is 2 feet. So I might come back to that picture, but I'm going to move on to what I'm trying to find. The rate of change of the radius when the radius is 2 feet. So you have to be careful here, this keyword rate, and then I guess altogether rate of change of the radius. It's not just asking for the radius. We're actually given the radius is 2 feet at a certain stage in this pumping up the balloon. So that kind of doesn't make sense anyway, but just look at that we are finding a rate, and that is a derivative. So we're trying to find dr over dt. We'll say when r, the radius, is 2 feet. So it's a little weird to say when and then give a dimension, but you know, this is what's given. It's not a particular time. That's pretty much what we've been doing lately, is that t equals 1 second, 2 seconds, that kind of thing. So this is a little different than we're supposed to figure out this rate when a dimension is a certain amount. Alright, moving on. Some of the given. or things we know. The picture helps with that, and maybe if something's in the picture you don't have to write it down. But one thing that we're given is this 4.5 in units of feet cubed per minute. And so here we should define what that is in terms of variables. So, kind of like we did with the dr over dt. Although that you're not going to have to worry about the units in terms of converting units and that kind of thing, everything will be set up for you and work out. The units do help to give us a clue about what our derivative should be. We have feet cubed per minute, so we have length cubed, which is in units that volume would have. And so this looks like dV over dt, the rate of change of the volume with respect to time. So the units can help you with that a little bit if it's not obvious from what is being said in the problem. So that's dV over dt, and that's given. So I think we have enough to move on to the next step, which is find an equation or equations, and they need to relate our dV, where we look at the rates stripped down without the rate part, and so we need to relate V, which was a given rate, and also what we're trying to find stripped down of its rates. So take off the derivative part, and what you'd be left with is R. And so this is what we're trying to find. So the equation we want has V and R in it. And so think of an equation that relates V and R that has to do with a spherical balloon, and you may arrive at the volume of a sphere. So that equation is V is equal to 4/3 pi r cubed, and note that it relates V and R. So before we do this derivative step, it's important that you think of what happens with time in the picture. So we're pumping the balloon full of air, and so the volume is increasing in the balloon, and then also the radius is getting longer because the balloon is expanding with pumping the air in. So what I'm trying to get at here is that V and R change with time, and so that therefore they're variables. That means I can't plug in, for example, R equals 2 in the beginning of this problem before I take the derivative, because that would imply that it is always 2, and the radius is not always 2 in this problem. So we can't plug it in yet. It's something we're going to plug in at the end after we do the derivative step, and that's going to come into play when we're figuring out the rate dr over dt, specifically when R equals 2. So it's kind of like when we were finding the velocity at time equals 2 seconds, you weren't allowed to write in t equals 2 in the beginning of the position function and get a constant and then take the derivative and get 0. It's implying that at t equals 2, it's not, you can kind of think of that in that way, that you're not going to plug that in first and then take the derivative. You got to wait for that part at the end because time is the variable. Alright, so anyway, kind of getting distracted there, but notice what we have are the variables V and R, and that's it in this equation. They both vary. When we take the derivative, it's for sure going to produce a rate for V and R, and then maybe some leftover stuff too with V's and R's, and we're prepared for that. So you take the derivative of both sides with respect to t, because we know the stuff in the equation that depends on V, and what we're trying to find is the rate dr over dt, so we need to introduce that somehow, and the way we're going to introduce that rate is to take the derivative of both sides of this equation with respect to t. Alright, so this is just saying, hey, I'm going to take the derivative of both sides, now actually doing it. We're doing implicit differentiation, where v is like the y and the t is like the x, although we don't have any t's that are going to appear in this equation. So it's like every variable that depends on time is sort of like the y that was in our implicit differentiation section. So anyway, the derivative with respect to t of v, when v depends on t, is just dv over dt, because it's just v by itself without being a function of v. Next thing, we take the derivative of the right-hand side. So this is actually not too bad here. I got a constant of 4/3 pi, and then taking the derivative of r cubed implicitly, where r depends on t, we take the derivative with respect to r, which will be 3r squared, and then we have to remember to multiply that by the derivative of the inside function r that depends implicitly on t as dr over dt. We're using the chain rule here. So now the derivative step is done, and in the last step you're just going to sub in and solve. So what we have here, well, we have dv over dt that was given as 4.5. Don't really have to worry about the units, they're just going to work out here. dr dt, you're trying to find that, so the fact that we don't know it is a good thing. And then r, we're supposed to do this when r equals 2 feet. So now I can plug that in. Excuse my cheesy ringtone if you heard that. We'll have to wait. So anyway, note that we can just plug everything in now and then just do some algebra to solve for, well, let's cancel these 3's first actually, for what we're trying to find, which is dr over dt. Okay, so we get 4.5 divided by 16 pi. So it's kind of a weird answer, combination of a fraction and a decimal. So just writing your approximate answer for these word problems is fine. And you should get about 0.09. Units are optional, but worth mentioning that the units would be feet per minute.